start there. Oh. Here we go. Okay, so yesterday we started tension. Tension exists in ropes, cables, strings, that kind of thing. We went through a couple examples, one involving rolling objects, no friction, one involving friction. The thing you want to remember here is that when these things, because they're attached by a rope, they're going to accelerate as a system, assuming that there is tension, not what Manuel suggested yesterday where the front wheels fall off and then this cart catches up with this cart. Like, that's going to mess everything up. As far as these problems are concerned, we're going to assume that they're accelerating or decelerating as a system. And so when we're looking for the acceleration of the system, we treat both blocks as if they were one large block. When we're looking for the individual tensions, we can isolate either block given the acceleration that we have. So we did that with these guys and no friction. We did that with these guys as an example of one of these things, including friction. If the wheels fell off this guy too, then the only thing that would be added to this problem would be what? There'd be friction on both blocks. And there'd be an additional friction here to, like, the friction on this guy would also be to the left. So it'd be there would be another term that would show up in here. Then we brought in pulleys. Pulleys are just designed to, Harshan, good morning. Pulleys are just designed to redirect the force. You can build all sorts of contraptions using pulleys to lessen the force required to do a certain job. But we're talking about simple pulleys, not those complex pulleys. So once you've done your free body diagram on the pulley to actually go through and then solve the problem, you lift the thing off and you stretch it so that it's flat. So now we've got FG and these two different FGs. They're actually, when we take it off the pulley to solve the problem, they're actually going to be going left and right instead of down, because this is actually what's happening. But to simplify the problem, we redraw it like this. So that's effectively all you missed yesterday. We were in the process of going through this example here using these masses 6 and 4. We were almost done, and then the bell went. The tension in the string is what we were looking for here. Did anyone calculate this final value, and then I just didn't take it from you before we left? What is that final value? $47.04. Okay, cool. Yes. Yes, I am. So what we did was, and we used the 6 kilogram block to isolate for that. Again, we could have used the 4 kilogram block as well. It would have given us the same value for tension. I proved that once already. Does anyone want to see that again? Or are we cool with kind of the procedure? I had a few more away yesterday. Cohen, you were away yesterday too. I'm going to go over it as well. Okay, I'll prove it again. So this one, the tension in the string, we isolated. This was isolating the 6 kilogram block. So let's go over, I'll do it over here in the bottom where I've got a little space. Let's isolate the 4 kilogram block. If we're going to do that, let's look at this block here. Again, we're starting with F net. What are the forces acting on that block? There's going to be an FG. No, there is no normal force.
Oh, sorry. No,
it's not sitting on anything. Just tension and gravity. So I've got FG acting to the right. So we said that to the left was positive, if you remember yesterday. So this one's going to be FT minus FG equals MA. So then it's going to be FT minus 39.2 is equal to 4 times 1.96. Jasmine, you did the previous calculation. Why don't you do this one too? What is FT if we isolate the 4 kilogram block? And again, it should be the same because this is the same rope attached to the 6 and the 4. This is the one that we're analyzing here. It is the same? Cool. So it doesn't matter which block we isolate. Both are valid. And you don't, and again, should I ask you on a test or a quiz to solve for tension? I don't need to see both. I'm just proving to you that the tension is the same everywhere in this single rope. So when solving for acceleration of the whole system, sorry, where did my notes go? We consider the total mass. We treat them as one. When finding tension, just like before, James, good morning, we find T only using one mass. So, flip the page. There's a couple more examples here. So this is slightly different. Now I don't have a hanging mass. Now I've got, well, I don't have two hanging masses. I've got a pulley allowing one mass to hang off the edge of a table and one mass to sit on top of the table. We want to find the acceleration of these two masses, and we want to find the tension in the rope. Now, what does your intuition tell you is going to happen in this situation? Connor.
Well, assuming it's those two blocks start stationary, like there's no given acceleration to them.
So yeah, I'm not tapping one.
Mm-hmm.
I'm not tapping one, like it's not moving. Okay.
And I think they might not move.
You're suggesting that they won't move. Why?
Well, because already the pulley is kind of taking off the main weight of the 6 kilograms, or the kind of the newtons there.
What do you mean it's taking it off?
It's supporting it. So it's supporting the block. So
But is it holding it back in any way?
No.
So what's happening, because you're right, it is supporting it, but again, all pulleys do is redirect forces. So this object here is going to have, there's going to be Fg acting down on this thing, right?
Yes.
So because this pulley exists, it's going to allow this 6 kilogram block, the Fg from this 6 kilogram block, to act through the tension here. It's going to act on the rope, causing tension to act on this block here. Why are you suggesting they won't move?
Well, because the 8 kilogram block will be heavier, and it'll have okay, so it's frictionless table. So
The table has no friction.
So yeah, it'll move.
So now you're suggesting it'll move. Because there's nothing holding this thing back.
Yeah.
Okay, so it doesn't matter what the mass of this 8 kilogram block is. If there is truly no friction, if the coefficient of friction between these materials is 0, and there is no friction, it doesn't matter how heavy this thing is going to be, it's going to move. That is a true statement. So let's go through and analyze it. We're going to do this twice, once frictionless and once with friction. In fact, I don't give you the coefficient of friction. I tell you what the friction force is. So let's go through and do this. What are rather, the forces that are acting on these two blocks? Let's draw the free body diagrams. What's happening?
Gravity.
I've got Fg acting on both. And let's actually just go through and do the calculations. Here, Fg is going to be what? 58.8.
And 78.4 on top.
Okay, what other forces are acting on these blocks? On which one? The 8 kilogram block has a normal force because it's actually sitting on a surface, and we know that the value for that is also going to be 78.4 because it's opposite gravity. What other forces are acting on here? Tension. Which block are we analyzing first? Okay, the tension on the 8 kilogram block, Jasmine, is which way? It's to the right. So that's going to be Ft. And on the 6 kilogram block, tension is going to be acting which way? Up. So then which way do we want to consider positive in this system? For the 8 kilogram block, or for the 6 kilogram block, or for both?
I think we could have two directions.
No, we want one direction.
I'd take the right then for the 8 kilogram block.
Remember, if we're going right for the 8 kilogram block, what's that going to mean for the 6 kilogram block? And remember, because the pulleys change the direction of the forces, it also is going to change the direction of what we consider positive. So when on a pulley question, when you've got something like this, if you want the 8 kilogram block to be positive, you've got to extend that over the pulley. So it's going to make that direction positive, to the right and over and down. That whole motion is going to be considered positive. This is still a one-dimensional question because the pulleys just allow us to bend dimensions. So then what we can do is we can redraw this thing. We can redraw this thing looking like this. This case, we're going to have FG equals 58.8. We're going to have an FT. We're going to have an FT. Then we're going to have an FG downwards here of 78.4. We're going to have an FN here of 78.4. So then to find the acceleration of the masses, I'm just going to use F net equals ma. What are the forces acting in the direction of motion of the system? Oh, and you guys said that way was positive. Sorry? I'm going to have two tensions, and I'm going to have, sorry? This gravity over here, the 58.8 newtons, is acting to the right because of how it was laying over the pulley. So one of these tensions is going to be negative, that one, and they're equal and opposite. We know that. So F net is going to be Fg minus Ft plus Ft equals ma. Those two tensions are going to cancel, so I'm going to get 58.8 is going to equal to, again, this is the total mass of the system. So this is going to be 6 plus 8 times A. What's the acceleration of the system? Is it exactly 4.2? Cool. Revenue, was that you? Thank you. So we've got an acceleration of 4.2 meters per second squared. And now I want to find the tension in the ropes. Or in the rope, rather. There is only one. Which block do you guys want to use? The right side? Why the right side? Sorry?
Is there a reason that you want to do it?
There's a reason I want to do the other one. Well, I'm just asking why you want to pick the right one. It's totally arbitrary.
Yeah.
Luis? Why might the left one be better to do? The only force acting on the left block in the direction of motion is Ft, which is what I want to find. So it's not a lot of extra, like I'm not reducing my work by that much, but to only deal with one force instead of two removes the chance of a simple algebraic mistake. I mean, it's a pretty simple algebraic expression, so maybe that's not an issue for you. You can do either one. I want to do the left one. So we're going to use F net equals ma, just isolating this block now. So I'm going to use Ft, because it's acting to the right, and that's what I said was positive, equals, now that is an 8 kilogram block, times the acceleration of the system is 4.2. So then Ft is going to be 33.6. Is that right? And we're done. So assuming a frictionless table, that's what we've got, but we know tables aren't frictionless. So let's analyze the same thing again using friction this time. The masses are the same. This is the same setup, except the only difference now is we've added in friction. So how's that going to change? That one's toast, and I keep using it. That one's toast, and I keep using it.
Assuming,
Orange it is.
and we assume it's the table that has the friction, not the pulley.
It said, oh, that's a good point. The question says the same system has a friction force of 25 newtons acting on the 8 kilogram mass. So because it's acting on the 8 kilogram mass, we can safely assume it's not the pulley. In fact, we will always assume pulleys are frictionless unless explicitly told otherwise. So I'm still going to have an FG acting this way of 58.8. I'm still going to have FT acting up on this block. I'm having FT act to the right on this block. And again, these are the same FTs because that is the same rope. I'm going to have an FG acting downwards on the 8 kilogram block. It's still going to be 78.4. I'm going to have an FN acting here of 78.4. And now we're told that there is a friction force of 25 newtons acting on the 8 kilogram mass. That friction force is going to be acting which way? To the left. Why to the left? It's because it's going to oppose the applied force. In this case, the applied force is the FG from the second block. So friction is going to be acting this way, and we're told the value of friction is 25 newtons. I will not tell you the force, likely tell you the force of friction. I will give you a coefficient of friction and expect you to find it. It's easy to do, though, because it's just going to be mu times Fn, which we did yesterday again, just a bit of a review. So the acceleration of the masses now, I can redraw this thing, and we're going to call the same direction positive, down and over the, or over and down the pulley. So I can pop these things off, redraw them. I'm going to have FG 58.8. I'm going to have FT acting that way. I'm going to have FT acting that way, and I'm going to have a force of friction of 25 newtons acting that way. I've got FG acting down that way of 78.4, and I'm going to have an FN acting up here of 78.4. And we said if over and down was positive, because that's the way this thing wants to move, in my redrawing of the system, that direction is positive. And I'm just going to go through and I'm going to solve this thing here. I'm going to start with F net equals MA. For the system, because it's the system that's accelerating. So then my F net expression is going to be similar to what it was before. The only difference now is I have friction acting to the left. So what is my F net expression going to be? But I'm not adding friction, I'm subtracting friction because it's acting to the left. So it's going to be FG minus FT plus FT minus force of friction. I'm just going in order here from right to left. FG is acting positively, that one's negative, that one's positive, that one's negative. And that's going to equal my total mass, which I'm just going to call M big T, times A. And now I can fill this thing in. That and that are going to cancel, so I'm going to get 58.8. I should have left a little bit more space here. Minus 25 equals my total mass of 14, the 6 plus the 8, times A. And I'm going to get a value now for A of what? We expect to be bigger or smaller than what it was previously? We want it should be smaller because now we've got friction acting against us. So what's the new acceleration? 2.414? Is that what it rounds to, or did you just cut it off? Okay, round it. Okay, so the next one's a 2, so then this is rounded. Can someone verify? Yeah, okay, nah, accurate, love it. So now the tension in the rope, again, now we can analyze one block. Now, Manuel, it doesn't actually matter which one we use because both blocks have two forces acting on it. So Manuel, which one do you want?
Right side.
The right side. Okay, cool. So F net equals MA on the right block. Which forces are acting positively? Which ones are acting negatively on that block? FG is acting positively, FT is acting negatively. Kenor, good morning. So it's going to be FG minus FT equals MA. FG was 58.8 minus FT, which is what we're looking for, equals 6 times the acceleration of the system. Oops, sorry. FT equals what? Can't remember, just finishing the examples from yesterday. I want the number, yeah. I'm waiting for the number. Sorry? 44.35. Can someone verify? 3-4 what? What's the next number? There's nothing. Okay. There it is. There is my tension, which again is now larger, which we expect it to because friction is going to cause this rope to be pulled harder to accelerate the system. And that's it. Comments, questions, concerns. The examples I did all had two masses in the system. If I'm not mistaken, I'm going to get you to do, oh no, they all still have two. When you revisit this in Physics 12, because you will, briefly, you will be given systems with more masses, and they will be more complicated and convoluted, and they'll be delightful. But for the time being, I want you to try these guys here. The answers are provided for you. There are two sets of questions. Let's see. Yeah, I want you to try all of them. On your market, say giver.
Yeah. So
Just 2 pages. This guy here and this guy here.
this was the only day I was in the elevator, and then I was like, hey, yo, physics.
Yes, the elevator is coming. The elevator is coming.
Oh, I haven't been in the elevator in a minute. That was cool.
Talk about elevators shortly.